You ever just stop and think about how wild the internet is? Seriously, you click on a link and faster than you can blink, a piece of information from a server that could be thousands of miles away just appears on your screen. It feels like total magic, right? But it's not. It's engineering, and it all follows this incredibly detailed plan. So, let's pull back the curtain and see how the internet actually works. Yeah, let's start right there. You're scrolling, you see something you want to check out, and you click. That one simple action, it kicks off one of the most complex, high-speed processes in the entire world. That click of yours, it creates a message. And that little message is about to go on an insane journey. It's going to zip across continents, maybe dive under oceans through massive cables, navigate a maze of routers, all just to grab what you ask for and bring it all the way back to you. But here's the thing. This whole journey isn't just chaos. It's not a free-for-all. It follows a really strict set of rules, like a secret blueprint that makes sure every single phone, laptop, and server on the entire planet can speak the exact same language. This is the bedrock of how it all hangs together. And this quote just hits the nail on the head. We all use the internet every single day. But for the next few minutes, we're going to swap hats. We're going to think like the network engineers, the people who actually build this thing and see it all from the inside out. So let's rewind to the 80s. The digital world was a mess, kind of like the Tower of Babel. You had computers from one company that absolutely could not talk to computers from another company. It was a nightmare. The world desperately needed one common standard. The two big ideas on the table were OSI and TCP/IP. By the 90s, TCP/IP had pretty much won, mostly because it was more flexible and developed by a community of volunteers. It's the reason everything just works today. So, what even is this TCP/IP model? Well, the best way to think about it is like the blueprint for a house. The blueprint itself doesn't hammer any nails, right? But it gives the plumber, the electrician, and the builder a shared plan so that the pipes don't run through the electrical sockets. TCP/IP does that exact same thing, but for all the different pieces of the internet. And this blueprint is neatly organized into 5 different layers, where each layer has one very specific job to do. At the very top, you've got the application layer. That's where your browser lives, creating the message. Right below that, the transport layer makes sure the whole conversation is reliable and nothing gets lost. Then there's the network layer, which is basically the internet's postal service. It handles the global addresses and routing. The data link layer is all about getting the message to the very next stop in the chain, say from your laptop to your Wi-Fi router. And finally, at the bottom, the physical layer turns all that digital data into actual pulses of electricity or flashes of light to send over a cable. Okay, now here's a little piece of insider info you gotta know. Even though the whole world runs on that 5-layer TCP/IP model we just saw, you'll still hear network engineers talk about the older 7-layer OSI model's numbers. It's like a historical shorthand. So if someone says, oh, that's a layer 3 problem, they just mean the network layer. Or a layer 7 firewall is working at the application layer. It's a little weird, but it has definitely stuck around. All right, so we have the blueprint. Now let's get to the cool part, watching our message get all packed up for its big trip. As it travels down through those layers, it gets wrapped up in more and more packaging. This whole process has a name. It's called encapsulation. So it all kicks off right here at the application layer. Your web browser creates the actual data, the message itself. In this case, it's an HTTP request, which is just a technical way of saying, hey server, could you please send me the file for this web page? Your browser then hands that request down to the transport layer. This layer is like a super careful packer. It takes your request and wraps it in something called a TCP header, which has info for making sure the data arrives safely. This newly wrapped up unit is now officially called a segment. Next up, that segment gets passed down to the network layer. This layer adds another wrapper, the IP header. This is like putting that segment into an envelope and writing the full to and from addresses on it, the global IP addresses. And now it has a new name. It's a packet. And for the final step before it hits the wire, the packet gets passed to the data link layer. This adds one last bit of packaging, an Ethernet header and trailer. This is like the local delivery instructions, just for the very next stop on the journey. This whole thing, all wrapped up and ready to go, is now called a frame. So let's lock in those terms real quick because they're important. At the transport layer, we call it a segment. Once the network layer adds its header, we call it a packet. And after the data link layer does its thing, we call it a frame. Each name tells you exactly how it's been packaged. So our message is packed up, it's addressed, and it's ready to ship. Now it's time for the network layer to really shine. And honestly, it works almost exactly like a massive worldwide postal service. I mean, the analogy is just perfect.
An IP address is literally the digital version of your home's mailing address. It's a unique location out there on the global network. And a router? That's just a post office. It's a sorting facility that figures out where to send the mail next.
So the key job of a router is actually really straightforward. It gets a packet, it glances at the destination IP address on the outside of that packet, it checks its internal map of the internet, and it just forwards the packet to the next router in the chain. That's it. It does this over and over, hop by hop by hop, all the way across the internet.
Okay, we've got the addresses and we've got the post offices. But what about the actual roads that connect everything together? How does our little frame physically travel from one place to another?
Well, for the most part, there are two main kinds of digital roads. The most common one you've probably seen is the classic Ethernet cable. It uses copper wires to send data as little electrical signals. It's perfect for shorter runs, like inside your house or an office. But for the really long hauls, like across a city or under an ocean, we use fiber optic cables. These send the exact same data, but as pulses of light through incredibly thin strands of glass. Now, besides the IP address for the long-haul journey, there's another super important address that's used for the local hop-to-hop delivery. It's called the MAC address. Think of it like a permanent serial number that's literally burned into every single network device ever made. So if your IP address is like your home address, which can change if you move, your MAC address is like your fingerprint. It is permanent and unique to you. And just how unique are we talking? Well, the system allows for over 281 trillion possible addresses. That is a mind-bogglingly huge number. It basically guarantees that the network card in your phone has a MAC address that is completely different from every other device on this planet. It's a pretty incredible system. So our frame has done it. It's crossed the globe, it's arrived in the right city, it's on the right local network. Now for the final mile. How does it get from the local router to the one specific computer it was meant for? This is where you can really see how much the technology has improved. Back in the day, networks used things called hubs. A hub is dumb. It's like a megaphone. When it gets a message, it just shouts it out to every single device that's plugged into it. It's loud, it's inefficient, and it's not secure. Modern networks use switches, which are way smarter. A switch is more like a telephone operator. It looks at the destination MAC address on the frame and creates a direct, private line only between the sender and the one device that's supposed to get it. It's faster, it's efficient, and it's way more secure. And that's it. From your simple click, your message followed that 5-layer blueprint, got packed into a frame, was routed across the world like a piece of mail, and was delivered to the exact right device on the other side. But here's the thought I want to leave you with. This amazing blueprint, TCP/IP, was designed almost half a century ago. It was built for a world that we would barely recognize today. So the real question is, what should the internet's blueprint look like for the next 50 years?